Hello and welcome to the 109th IUVSTA workshop, the APPEC Technology Forum, Vacuum Cryogenics, where industry meets academia. Today we will have a short teaser by one of our invited speakers, Thomas Tümmler, who will report on experiments searching for the mass of neutrinos.
So hello and thank you for having me here. My name is Thomas Tümmler from the Institute for Astroparticle Physics of KIT. My field of research is neutrino physics and especially neutrino mass determinations from the tritium beta decay. I'm here today to introduce you to the upcoming challenges in our present experiment, the Catherine experiment, and what is coming next in Project 8, QTNM, and finally in Ptolemy. But let's get started right away. The Catherine experiment. Well, this is the experiment we have here at KIT. This is the world-leading neutrino mass experiment based on single beta decay. We have a strong molecular tritium source, a 70-meter long beamline, and maybe the largest ultra-high vacuum chamber you can think of, a 1200 cubic meter large main spectrometer. It took us about 15 years to develop all the technologies and the diagnostics and operational parameters to run this experiment. And since now 6 years, we are taking data, but we have to think of what is coming next. And the things we have in mind for our next phase is we would like to change the integral measurement principle into a differential mode. That involves time of flight measurements, that involves beta electron tagging. And finally, this will then be immune to some of the backgrounds that are currently limiting us. On the other hand, at the other end of this detector, of the spectrometer, is the detector system. So the detector system is currently only counting electrons, and we rely on the filter performance of the main spectrometer. This is the McE filter principle. But for future applications, we want to have a detector system which is able to resolve the beta spectrum much finer, and therefore we want to try to apply microcalorimeters, and therefore we have to operate them in the magnetic field, and we have to couple a cryo platform at the millikelvin level to a room temperature spectrometer. Well, so far on the Catherine side, but there's more than that. The main uncertainty in such kind of experiments is the fact that we are using a tritium gas molecule. If this decays, the molecule ends up in rotational vibrational states, and that's a limiting factor. In order to get rid of that, we have to crack this molecule apart and only observe decays from atomic tritium. This sounds simple, but it isn't in the end, because we have to supply a lot molecular tritium. We have to crack that at temperatures of up to 2500 Kelvin, then cool it down in order to trap or inject the atomic tritium into our measurement device. So this will then lead to the next generation of experiments, which is Project 8 and QTNM. Project 8 pioneered a method that is not relying on detecting electrons with a semiconductor detector. Project 8 uses the cyclotron radiation that is being emitted from the electrons when they are traveling in a magnetic field. If you do that, you get a very distinct shape and pattern of your emission, and you can determine the energy from this frequency measurement then with very high precision. You can discriminate backgrounds quite perfectly, but you need a quite different approach to your spectrometer. This is pioneered by Project 8, and QTNM is applying these principles. The approach of QTNM, which is the quantum initiative in the UK, is to inject these atoms into a small storage ring and then apply quantum sensors to determine or to catch the cyclotron radiation, which is emitted at each revelation of the electrons in the trap. So here's a lot of vacuum and cryogenics and magnet development involved. And then finally, these signals are identical to what Project 8 is recording. Project 8, on the other side, is using a magnetic trap, a gravitational magnetic trap, in this case shown here, to gather enough atomic tritium inside the trap so that you get a sufficient amount of decay electrons. These are then stored as well in this magnetic trap. We record the cyclotron radiation that is being emitted, and that's the basic principle. The thing is that this vessel then is a cryostat at very low temperatures with a sophisticated magnet design, and at the same time you have to crack enough tritium, cool it down, and inject it into the trap to keep the count rate stable. And then finally, in order to go beyond the sensitivity of the Catherine experiment, you not only need one of these experiments, you need 10 of these towers, 10 meter high, 2 meters in diameter. Beyond that, on the horizon is the Ptolemy experiment. This is not so much aiming to measure the neutrino mass, but they are trying to directly detect neutrinos that are the remnants of the Big Bang. Like we have the cosmic microwave background, there needs to be a cosmic neutrino background, which is very difficult to determine. So this really goes by orders of magnitude beyond that what Catherine Project 8 and QTNM can do. All of the key technologies we are currently developing or that have been developed over the past years need to be applied here from a target based off a graphene lattice loaded with atomic tritium. Then in one part where you have RF antennas to measure the incoming electrons. A transverse energy filter for fast tuning. And finally, a microcalorimeter to detect the electrons. All of these things still need to be developed and are really cutting edge. And that brings me to my point in the end, which I wanted to emphasize, is that between the predecessor experiment of Catherine, the Mainz experiment, and the start of the Catherine experiment, we spent about 15 years of developing technologies. So now we are coming to an end of data taking with the Catherine experiment, and the next experiments are on the horizon. If you then imagine that we have to spend the next 10 to 15 years to develop technologies and commission completely new approaches to get these experiments running, there's one thing that is really essential, and that is a strong partnership between industry and our scientific staff. And yeah, I would like to invite you to my talk at the Tech Forum, and thank you for your attention.
Thank you for listening to the short introduction to topics of our 109th IUVSTA workshop, and we hope we can welcome you in Maastricht at the meeting on November 24 to 26.